This is the fourth lecture, and in this lecture I'll talk about another analytic method for solving differential equations, and this is called the method of undetermined coefficients. Now this method of undetermined coefficients, again, is used to solve linear non-homogeneous equations. In the previous lecture we used an integrating factor to solve these equations, but then there were several integrals. This is a different method. It solves the same kind of equation, but it avoids all those integrations. It doesn't work all the time, but when it does work, it's a very handy tool. First, let's write down for review what we've done so far. We had separation of variables, and in that case we needed the differential equation written like this: some function of y times some function of t. One of these could be a constant, the g of t could be a constant, of course, and the y could be very nonlinear. That was the first method. The second method was the integrating factor method, and we had just the linear differential equation like this. And when we solved by this method, we had an integrating factor, which was e to the integral of p of t dt. And some people say you should rederive all the steps. I don't think that's too necessary. Once you understand the method, it really falls right out. The solution equals the integrating factor with a negative sign here times the integral of the integrating factor again times the forcing function q of t dt. And you have these two integrals to solve, one in an exponent, and then after that you have to deal with the other integral, and they might be tricky. You might not be able to solve them. So now we're going to look at the method of undetermined coefficients. So in this method we're going to use the principles of linearity from lecture 2. Let's recall the principles of linearity from that lecture. First, there was one called principles of superposition, which is meant if you had a solution to a differential equation, a homogeneous differential equation. I'll write it as linear here. Doesn't necessarily have to be linear, but if you had a solution of this equation, then some constant times that solution that you had will also solve the same equation. If you had a second order equation and you had two functions, I'll just put a square up here to solve that, then y of t would be something times the first solution plus another constant times the second solution. Okay, this principle works fine if it's a homogeneous equation. If it's not a homogeneous equation, we had two other principles of linearity called the extended linearity principles. The first extended linearity principle, again this is for the non-homogeneous equation, writing it like this: q of t for the forcing function, q of t not 0. Then we could take the complementary solution, which is the solution of the same equation with q of t set to 0, and then we could take the particular solution, which is the solution of the equation with the same equation with q of t not being 0. So q of t, I should put the p's here, solves, the particular one solves when q of t is intact. When q of t is set to 0, then the solution is the complementary solution, and you can add those two together and get a solution for the differential equation. And that is the first extended linearity principle for non-homogeneous equations. We're going to make use of that. But first I'll just give the idea or a mental picture to go with this method of undetermined coefficients. I use the analogy of a swing in the written lectures. So you're pushing someone on a swing and you push at one push every 5 seconds. Then after a while the swing will start to oscillate at one push every 5 seconds. Maybe if you weren't around, the swing would move in a much different way, but if you keep pushing that, you are the forcing function in that condition, in that situation, then it will start moving at one oscillation every 5 seconds. If you slow down your pushes and you start pushing at one push every 7 seconds, then after a while your forcing function will entrain the swing so that the swing will start operating at one oscillation every 7 seconds. And that's the idea. When you have the forcing function q of t, you're going to find a particular solution that's very similar to it. It's going to have a very similar form with some coefficients that are undetermined, hence the name of the method. But before you choose the particular solution, first you have to take a look at the complementary solution. If the complementary solution and the forcing function are the same, then you have to do things a little differently. If they're very different, then you can use what I'm going to show you in the next slide. So the first step in using this method is to find the complementary solution. Now let's say you found the complementary solution. For example, say y of c was e to the 4t, and your forcing function is sine omega t. Okay, they're sufficiently different that there's no that you can't say q of t is a linear combination of this. So in that case you're going to use this table. There'll be a table 2 when they are the same. So if the forcing function and the complementary solution are very different, then you model your particular solution after the forcing function. So if the forcing function is exponential e to the beta t, then you would have your particular solution be e to the beta t but multiplied by a constant a coefficient a. Okay. Now if this forcing function is a polynomial, then the particular solution is also a polynomial of the same degree but includes all the terms down to the constant. Now let me show you why that is so. To use this method, you're finding a particular solution. You're assuming it has this form, and you have to find values for the a, b, c, or d, or not in this case. You say, well, why bother? I'll just go like this. I'll show you what happens. This example also shows you how you evaluate those constants. So here's my differential equation, say dy by dt plus 12 y of t equals, what was my e to the beta t? Okay. No, I'm sorry, I was doing something different, wasn't I? Okay, let me erase that and try it again. Excuse me. dy by dt plus, say, 12y of t equals 3t squared. Alright. So first I look for the complementary solution. And the complementary solution here is just obvious. You should be able to see that in no time at all, because what derivative would be the same as the function? Only the exponential is the same as the function. And why would you have a constant in front of it? Because of the chain rule. So y of t, this will be the complementary one, equals e to the minus 12t. Right? If I take the derivative, the minus 12 is in front, and then the next term is e to the minus 12t. Okay, so I look up here at the 3t squared and I say they're very different, so I'm going to go ahead and model my particular solution directly after the forcing function. Okay, I have to rewrite this, but that's okay. So I've got dy by dt, what was it, 12y of t equals 3t squared. So the complementary solution was e to the minus 12t. Okay, and our q of t is 3t squared. What happens if I say I'll just let the particular solution be some constant a times t squared, and why bother with those others? Well, this shows you also how you have to choose those or evaluate the coefficients. So to evaluate the coefficient, I take this y of p and I put it back into this equation. So when I put it back through the equation, I'll get, taking the derivative here, I've got 2a times time plus 12a t squared equals 3t squared. So now I compare similar terms. I will compare the 12a to the 3 here because they're both t squared terms and get a equals a fourth. Okay, now I have this equation. I can't ignore it, but what's that term over here? It's 0t, correct? So I would have 2a equals 0, so now I have another solution for a equals 0. And of course you can't have those two solutions for a, so this doesn't work. Now I'm going to try it again doing the rule that was listed in the table. So here's the solution, here's the equation again, sorry. 12y of t equals 3t squared. And this time I'm going to pick all the terms. A t squared, a t, and a constant term. Now put that through the differential equation. Taking the derivative, I have 2a times t plus b. That's for the derivative. Then I'll have 12at squared plus 12b times t plus 12c, and that equals 3t squared plus 0t plus 0. Now if I equate similar terms, I have the same. Okay, so again I get a equals 1/4. Now when I compare the terms that have t in them, I have 2a plus 12b equals 0. So now instead of just getting a equals 0, I have the b here to sort of help me out. I can use the value for a from above, and so that gives me 1/2 plus 12b equals 0. So now I get a value for b. It better be minus 1/24. Now I have an additional term here, 12, constant. I've got b plus 12c has to equal 0. That's from, okay, that's taking the constants here, and here's a constant, and that of course has to equal the 0 on the end, comparing the constant terms here. And of course I get minus 1/24 plus 12c equals 0. Okay, I'll have to think about this one. So c is going to be 1/24 times 12, which we can work out ourselves. Alright, now these are the coefficients right here, and I have determined them. And I didn't end up with two values of a. Looking a little further down the table, if q of t is either a sine wave or cosine wave of a certain frequency, which I'm just writing as omega, then the particular solution has to equal two terms, both the sine and the cosine, with the coefficients a and b. It's similar to this case where you had to give the entire polynomial. Here you have to give both sine and cosine terms, and the reasons are the same. And now the final row in this table demonstrates that second extended linearity principle. And this second extended linearity principle says that if your forcing function is several terms added or subtracted together, then you can find particular solutions that apply to each one and add those together later. So you can look at each one separately. So if I look at the 6 e to the 6t, and again this is a case where none of the forcing function looks anything like the complementary solution, e to the 6t, then here is what I would do for that particular solution, a e to the 6t. The next term is 12t squared. In this case, I'll use the polynomial, counting all the way down to the constant. And the third term is a cosine term, so I have a cosine plus a sine that ran off the end of the page. Okay, right in here is f cosine omega t. Okay, so I think I mentioned earlier that I have absolutely, well, probably a negative amount of artistic ability. So I apologize for things like this that are probably offensive to people who have artistic ability, that I would use such a color scheme. I'm just trying to communicate, and that's the best I can do here. Right, so the bottom line is that we use the second extended linearity principle to match up each piece. If they're multiplied together, then there's other ways to do that too. It's basically just about the same. Okay, so this is how you do it if the forcing function is not a linear combination of the complementary solution. So obviously we have to consider the case where it is. So look at the first line here. Okay, here's the complementary solution, and it includes e to the minus 2t, which is also included in the forcing function. If you want consistency here, these should be q of t's. Okay, the way to handle that is you let the particular solution also be a function e to the 2t, but you multiply it by t. In the case where it's already multiplied by t in the complementary solution, you have to multiply by t squared. The same is true if, say, the complementary solution is sine of, I don't know, 4t, and the forcing function is 12 sine of 4t. Then for the particular solution, you write a t sine of 4t plus b times t cosine 4t. Okay, like I say, it's not a real difficult method, and now I'm going to give you one example working through the steps with the RL circuit. So I'm going to use again the same circuit that I did in the previous lecture. In the previous lecture I had some kind of inductance, some kind of resistance, and I put a battery voltage, so it was just constant. It was just some constant voltage here. And now I'll replace that. So again I have inductance, some resistance, and I'll replace it with some kind of signal. It's like you took this and plugged it into the wall or something. Okay, and the signal is going to be some peak voltage times sine of t. In the written lectures I worked this out with sine omega t, and you can see there's omegas all over the place, and that's why I had to replace that lecture, because I lost my omegas in the solution. But here I'm just going to do sine t, and I'll show you where the omegas go. Okay, so I take that equation and I write it in standard form that we did before. So here is what I have: di by dt plus r over L. R over L is the p of t. Okay, and I'm looking for the complementary solution, so I set that to 0. And that's just what we did in this previous lectures. This again is the easiest equation to solve. This would be the complementary. So the complementary current here is e to the minus r over lt. You want to see where the negative sign comes from, put this term on the other side and you'll get the negative sign. Okay, so here's my complementary solution. Here's my q of t. They're dissimilar, so I can use table number 1. So here's what I have. di, this is the particular that I'm looking for, plus r over L, particular current, is equal to peak voltage over L. The reason there's an L is to get it in that standard form. sine of t. And I choose the particular solution, sorry, should be I of p, to be some constant a, some coefficient a, times sine t plus the coefficient b times the cosine of t. And now I have to determine the coefficients a and b. You see here we've done no integration at all to get this solution. So when I put this through the equation, I have to take the derivative. So I've got a cosine t minus b sine t plus r over L times a sine t plus r over L times b cosine t, and that has to equal Vp over L times the sine of t plus 0 times the cosine of t. And then I equate all the terms that are sine terms. I got a minus b here, and I have a r over L, and it has to equal this. Oops, that was an equal sign. So I have two equations. So here's the equation for the cosine. It'd be a plus r over L times b equals 0. That's for the cosine terms. And for the sine terms, I have the r over L times a minus b, and that has to equal Vp over L. So now you just have to do some algebra, and the end result is A equals the peak voltage times R over R squared plus L squared, and B equals minus Vp times L over R squared plus L squared. Okay, it doesn't take a lot of work, but you have to do some algebra, but you didn't have to do any integration, and now you have your particular solution. So I'll just write it here. Y of p equals Vp R over R squared plus L squared sine t minus Vp L over R squared plus L squared times the cosine of t. And the complementary solution, which was e to the minus r over lt. And now we put all this together. Y of t equals, you can multiply this complementary solution by any value, so I'll multiply it by c. C e to the minus r over lt, and I'm going to do something with c in a minute, and then I could take this out, and I've got r over r squared plus L squared sine t minus L over r squared plus L squared times the cosine of t. Okay, I want to point something out. If it were sine omega t, and this is one reason for not setting things equal to 0, but I did it for this demonstration here. But if it's sine omega t, the omega will appear here. You will end up, this term is going to be r over r squared plus omega squared L squared, and this term will be omega L over r squared plus omega squared L squared. But you see when omega is set to 1, how it sort of disappears from the equation. Okay, I just wanted to point that out. So now I'm going to do something with this constant c. So here I've typed out the combination of the complementary solution multiplied by constant c and the particular solution. We found all this by the method of undetermined coefficients. But I want to point out now is that we can evaluate c in terms of the initial condition. So typically here would be the equation. We had sine t here, and then the initial condition would be the value of the current at 0, which we'll just call I0. So now I'm going to take this whole solution and I'm going to run it through with t equals 0. And if t equals 0, then that equals I0, which is my initial condition, e to the 0 is 1, so I just get the c. The sine term is 0, and all I have is the cosine term. Then I can solve for c. Now, the reason for pointing this out is that you might think, well, I'm going to evaluate the c in terms of the initial condition, but you have to have the entire function here because these terms play a role in the value of c. The complementary solution by itself is not evaluated in terms of the initial condition. The whole solution is evaluated in terms of the initial condition, although the constant is only multiplying the complementary solution. So here's an analysis of the results that we got. Here's the solution right here, and we're going to have two terms again, a transient term. You can see this first term is transient. It includes this decaying exponential e to the minus r over lt. The second term is called a steady state term, but it's not the steady state term that we had in the other examples in the previous lecture. In this case, the steady state term is not a constant. It's actually a sine wave, and so it's called a sinusoidal steady state. And what this means is that, sort of do a graph of it. Here would be the steady state term, which is sort of a combination of sine and cosine waves, poorly drawn here, of course. And this is current, and this is time. The transient solution is some sort of decaying. Let's say it, well, it'll have to start at 1. Actually, it starts at this value, and it's decaying to 0. So these are added together. See, this transient will make the actual solution start at a higher value than 0. I started at 0, it would be a little bit off 0 actually, and it would sort of move down here, and eventually it would start looking like the forcing function. So the transient would have an effect early on in this very poorly drawn picture, and eventually the system, which would be the black line, would be I of t, would start looking very much like the solution, the sinusoidal steady state solution. So again, just to review what we did, we took a first order linear equation that was non-homogeneous, that had a forcing function. We set the forcing function to 0, and we found the complementary solution. Then we looked at the forcing function to see if it was a linear combination of the complementary solution. If it wasn't, then we could use table 1. If it is, we use table 2. The only difference between table 1 and table 2 is that when you pick the particular solution in table 1, you make it equal to the forcing function multiplied by some undetermined coefficient, a constant, following certain rules. If it is similar, if the forcing function is similar to the complementary solution, then you do the same thing, but you multiply it by t. The other rules were that if it's sinusoidal, for the forcing function, your particular function is a sine t plus b cosine t, with the frequencies being the same. If the forcing function is polynomial of some degree, then you make it also the particular solution that you're guessing is the same polynomial. It's of the same degree, but you count down, use all the terms in it. Then you take your particular solution, put it back into the original equation, and do some algebra. There's no integration at all. In fact, it is so remarkable that in this study of differential equations, how little integration there really is. In the next chapter, you'll see plenty of algebra and very little integration. It's kind of amazing. Okay, that's the end of this lecture.